Let us derive the expression for kinetic energy, which we know is the energy a moving object possesses, and it's calculated as half mv squared. Now, let us consider a mass m with some initial speed u, and I'm going to apply a constant force F on it over some distance s, and by the time it reaches its destination over here, its speed would have increased to v. Now, the first thing that we want to do, of course, we want to derive this expression of Ke using the concepts of work done. And so we want the work done by this force F over here to equal to nothing but the change in Ke. And therefore, it is very important to recognize that this surface over which you accelerate this mass must be both frictionless, so that there is no work done against friction, and it must be horizontal, so that there is no change in the GPE. And then we can, of course, say that, well, the work done by F is purely equal to a change in kinetic energy. And so let us go ahead and do that. So the change in kinetic energy is the work done by F, which is force times distance, Fs. Now, because this force is the only horizontal force acting on mass, then we can use Newton's second law to say that F equals to ma times s, right? So that over there is Newton's second law. But also, again, since the force is assumed to be constant, then this acceleration is constant. The mass is moving in a straight line, so we can use the equations of rectilinear motion. And so remember that v squared equals to u squared plus 2as. And so I can replace as over here with v squared minus u squared over 2. And so what do we get? We get, well, half m v squared minus u squared. And there you go. That is the expression for the change in kinetic energy. Typically, we say kinetic energy is simply half mv squared because we assume that the object accelerates from 0, or rather from u equals to 0, in which case half mv squared minus 0 is just half mv squared. But the more generic expression, of course, is half mv squared minus u squared for the change in Ke.